So the next speaker is Bibek, and you're welcome to share your slides.
Hello, everyone. Good morning. Do you see my screen?
Yes, we could see your screen. Can you go to the full screen mode or presentation mode?
Sure. Is it okay?
Yeah, that's perfect. It's your show, Bibek.
Thank you. First of all, I would like to thank all the organizers for this opportunity, and I would also like the organizers for such a nice conference. I'm Bibek Bhandari, a PhD student at Scuola Normale Superiore. I would like to present about our recent work on geometric properties of adiabatic quantum thermal machines, which is recently published on NITheP. This was a work done in collaboration with Pablo Terena Alonso and Liliana Aracchia from Buenos Aires. Fabio Tadei and Rosario Faggi are my supervisors from Italy, and Felix von Oppen from Berlin. So in this work, we took a n-level quantum system. So you can see, if you see my pointer, you can see where I'm pointing is our system, and this system is made of n-level and energy levels, and it is driven adiabatically. So, and this n-level quantum system is attached to two thermal baths. On the left, you can see there is a red bath, which I want to denote a hotter bath, and on the left, on the right-hand side, we have a colder bath, which is denoted by blue. So in this type of system, we can have different processes. First of all, since there are two thermal baths which are kept at different temperature, naturally a heat flows from the hot bath to the cold bath. And since there is a driving, adiabatic driving, we can have two different adiabatic drivings or even many different adiabatic drivings which differ by phase, and we can have pumping of heat from one bath to the another bath. On the same time, we also have dissipation of heat, and you need to supply some work to drive the system. And you can consider this simple setup as a heat engine or a refrigerator. So one can also have efficiency for these thermal machines. So since there are many thermodynamic parameters associated with the simple setup, what we tried to ask ourselves was what thermodynamic parameters have geometric origin. I will come to the question why geometric, why are we asking this geometric characteristic? And then we also asked ourselves, what is the effect if there are some thermodynamic parameters which have geometric nature? What is the effect of these parameters on the performance of thermal machines? And can we see this effect in some minimal quantum devices, all these geometric properties? So first of all, I would like to go to why I'm asking about why I'm interested in geometric nature. So if we, so a brief preview on this subject, here I have kept only the heat pumping one, but the first work, I would like to mention also the first work by Peter Brouwer, where he studied charge pumping in quantum dots by driving the quantum dot. So he had two different drivings which differ by phase, and while doing so, he could pump charge from one bath to the other bath. And this pumping of charge was independent of the nature of the driving. How fast or how slow you drive the system, you always got the same number of charge pumped from one reservoir to the other. On the same footing, so recently, there was some study on heat pumping, and what people observed was even heat pumping can be studied as an integral over the parameter space, in the sense that if you drive the system adiabatically and you somehow are able to pump heat from one side to the other side, then the amount of heat pump does not depend on how fast or how slow you go on the parameter space, but only depends on the contour you follow on the parameter space. And this was seen in the case of a two-level system, weakly coupled, using master equation by the group of Peter Hange, and even for the strongly coupled system with the spin boson by Wang et al., and even for quantum dot system by the group of Janin. And you see that the heat current, the expression of the heat current on the bottom part of the slide is given by an integral over the parameter space instead of an integral over time. So this is what we mean by geometric nature. So to clarify again, if I say something has a geometric nature, what I mean is that it can be written as an integral over the parameter space. So going back to the argument that I brought up in the beginning, given a quantum system, n-level quantum system, which is attached to thermal reservoirs, and provided the driving is done adiabatically, we already saw that the heat current that is being pumped from one reservoir to another has a geometric nature. Now, what we are interested in is, can we have other thermodynamic parameters that show geometric nature? And if so, what are the effects of these geometric parameters on the performance of thermal machines? So in the rest of the slides, I would like to answer these two questions. But to answer these questions, I would have to necessarily go into the microscopics. I would have to get the expressions for the thermodynamic parameters. So I would like to use the linear response theory, since we are considering adiabatic dynamics, and we only consider linear response also in the sense of thermal bias. So we have a very small thermal bias in the sense that delta T is very, very small compared to T. So we use the Kubo formulation, and we also use the Luttinger tricks to use Kubo formulation for thermal bias case, because as we know, the temperature enters inside the Fermi distribution or the Bose distribution. So one can't treat the thermal bias in the usual Kubo sense. So Luttinger came up with, the details are in the paper, but here I would not go into the details. I would just tell you what one can obtain after all that trick is that the bath Hamiltonian, as you see here, can be divided into two parts. The H bath here is with only one temperature T, so it is at equilibrium temperature T, and the thermal bias is included in SDST, thinking in a way that once in the way of electric potential. So one can think in this way: if you have an electric potential gradient, then you can have an electric current, right? So what Luttinger supposed was, if you have a gravitational potential gradient, then you can have an energy flow. And starting from that argument, what one can find is that the bath Hamiltonians with thermal bias can be represented in terms of these two Hamiltonians, where the thermal bias is included in SDST, and it is given by a product of energy current density times xi alpha t. And the time derivative of xi alpha t gives the thermal bias delta t alpha. So one good thing about this Luttinger formulation is that one can treat the driving as well as thermal bias on the same footing. What do I mean by same footing? So if you look at the driving is done, sorry, this is HS here. So driving is done with respect to XL, right? So these are X vector T which are being driven. So there are L equals to 1 to N terms which are being driven. So these are energy parameters which are being driven. And FL are the, excuse me. So, and FL are the forces associated with driving. Now you can say that, okay, I put L equals to 1 to N plus 1, and N plus 1 term of force is J alpha E, and N plus 1 term of driving is xi alpha T. So N plus 1 term in our driving would give the thermal bias as well as energy current density. So within this formulation, keeping the thermal bias as well as driving on the same footing, we arrive at these two results using Kubo formulation. So what Kubo formulation tells us is that the heat current and all the observables can be written in terms of response coefficients times velocities. So what I see is that the heat current, since we have thermal bias as well as driving, we have two terms for the heat currents. The first term is the heat current due to thermal bias, which is given in the top. So it is the N plus 1 term. X dot N plus 1 is the thermal bias delta T. And the second term, which is the pumped heat current, that is the heat current that is being pumped due to adiabatic driving from one bath to another bath. And this is given by this term here. And the driving here is XL dot T, which means the time differentiation of different energy parameters of the system. So after this, we would like to also define power, or the work that is being performed on the system. It's very easy to define power in this formulation. So what one does is, so power is defined as a product of force times velocities. So the force is FL for the driving, and for the case of thermal bias, we saw before that the force was given by the energy current density. And the velocities are XL dot for the driving, and for the thermal bias case, it is given by xi alpha dot T, which is at the end thermal bias delta T. So, but one would also it is also nice to remember that FL is an observable, and this observable can be written in terms of response function times velocity. So here what we find is that the power is a bilinear quantity in terms of velocities, because one velocity enters from here and another velocity comes from here, because every observable can be written as a product of response function times velocity in the Kubo formalism. So at the end, what we find is that power as well as heat currents are given by this thermodiabatic tensor, lambdas, big lambdas. And it's very nice that all the thermodynamic parameters can be characterized using studying these lambdas, starting from power, entropy, heat currents, and as well as we can go to efficiency. So first of all, I would like to study this lambda. How can we characterize lambda? It has been widely studied. I mean, the properties of lambda has been widely studied in the recent years. And first of all, one can break this lambda into symmetric and antisymmetric components. In the Lemon representation, the symmetric component is given by this term. And one point to remember is that the symmetric component has only one sign. It is only positive. It can take negative values. So it is related to dissipation and defines entropy production rate. And if there is no macroscopic phase transition, it is smoothly varying. It is positive semi-definite. So what does it do? It induces a Riemann manifold in the space of thermodynamic states. So if you have a Riemannian manifold in the space of thermodynamic states, what you can do is that you can have a definition for geodesic, right? So the geodesic gives you the geodesic in this thermodynamic state, in this thermodynamic space, gives you the path for minimum dissipation. So in a way, it enables the definition of geodesic that minimizes the dissipation. And correctly, it is also referred as geometric friction because it gives you the dissipation. And the antisymmetric component on the other hand, can take both positive as well as negative values. And it rightfully, it is not associated with any entropy production. And the curl of a vector field in the absence of thermal, it can be written as a curl of a vector field. And it is also referred as geometric magnetism in this sense. And at zero temperature, it corresponds to Berry curvature. Now, I would like to come to why we call this thing thermal geometric tensor. We call this thermal geometric tensor because we think that this quantity is a thermal analog of quantum geometric tensor. So if one looks for quantum geometric tensor, which is defined for a closed system, what one notices is that it defines a metric in the manifold of the ground state. And it is defined, so you have, and the antisymmetric component of this quantum geometric tensor it defines also the Berry curvature. So they have similarities, both quantum geometric tensor and this thermodiabatic tensor. The only difference is that the quantum geometric tensor is defined for discrete spectrum, whereas this thermodiabatic tensor is defined for continuous spectrum. So we call this lambda, the big lambda, as thermal geometric tensor in our case. Going to the next slide. So in the previous slide, what I did was a geometric characterization. I would like to also emphasize that geometric characterization would be different from geometric nature of the thermodynamic parameter. So when I say geometric nature, I would like to say again, I would mean that the thermodynamic parameter which can be written as an integral over the parameter space, I would say that that thermodynamic parameter has geometric nature. So in this slide, I would like to look at geometric nature of different thermodynamic parameters. First of all, let's talk about the heat current. So in the first equation, we see that the heat current is given by two terms. The first term is associated with driving, and the second term is associated with thermal bias. So the term that is associated with thermal bias can be seen as an integral over time because it's not associated with any there is no parameter space for thermal bias. But for the case of adiabatic driving, you can see that the heat current due to adiabatic driving or the pumped heat current is an integral over the parameter space. So what I can say is that the heat current due to driving is a geometric quantity. Now, when we go to power, we have one term which is bilinear in XL dot, and another term which is given by XL dot times delta T. So this is a cross term. But due to Onsager relation, I would like to emphasize that delta L comma n plus 1 is equals to minus delta n plus 1 comma L. So again, this term here is a geometric quantity because it can be written as an integral over the parameter space. So what we see here is that in the heat current, we have one term which is geometric, which is of geometric nature, and also in the power we have a term which is of geometric nature. But what about this term here, the first term, which is symmetric in LL prime, and it is associated with entropy? Does it have a geometric nature? So we find that if we have a mapping from x dot mu to x mu, which happens when you have like a piecewise harmonic system, or even for simple harmonic driving, you can have this mapping. If you have this mapping, then you can take one of this x dot and write it in terms of omega times a function of x mu. And at the end, you can get this expression. Yeah.
You have 5 minutes.
Yeah, I'm almost to the end.
Wonderful. Thank you.
So what you find is that you can write this x dot in terms of a function of x mu, and then use this x dot to cancel out this dt, and then you get an integral over the parameter space again. So let me go to the next slide, which is the last slide. You have this. The heat current is given by an integral over the parameter space when there is no thermal bias. If there is a thermal bias, we have a term which is not of geometric nature, which I showed you before, which is due to the thermal bias. But the power, on the other hand, both the terms are of geometric nature, in the sense that even the first term can be written as an integral over the parameter space, and the second term was we already saw that it could be written as an integral over the parameter space. So what we see is that the first term here gives you entropy production, and it's always positive, and it kind of ruins the heat to work conversion. So it is kind of a cost you pay. It's associated with the dissipation of heat. So by reducing this term here, the symmetric component, you can increase the efficiency of your thermal machine. So you can see that the thermodynamic parameters, which can be characterized geometrically in the very sense, helps in getting a highly efficient thermal machine. So it helps the efficiency of a thermal machine. And this was the general formulation, and we used this. We studied this general formulation in two different examples. The first example was the qubit weakly coupled to two thermal baths, and it was being driven adiabatically. For the pumping of heat, we had to take asymmetric spin coupling between the two baths. Otherwise, it's impossible to get a pumping of heat in the case of qubit. And for the case of strong coupling, we considered driven quantum dot attached to spin polarized leads. And we studied the pumping of heat, the power associated with driving, and the work done to drive the thermal machine. So, and we studied these geometric characteristics in these two examples. I'm sorry for the lack of time, I can't go into the details. If someone is interested, I invite you to read the paper. Thank you.
Okay, thank you very much for the very nice talk. And while people are thinking about this question, can I ask a first question? And sure. In your kind of, when you perform the kind of this adiabatic tricks, I always have a question with kind of, do you check that you still remain in adiabatic condition? Have you estimate how long, what will be the evolution of the time, or kind of what is the trade-off between the size of the gap and the, so kind of how you check that you are still doing the adiabatic, you're staying within regime of the adiabatic theorem?
You mean in the case of examples?
In the case of examples, for example, yeah.
Okay. So in the case of examples, I mean, for the case of qubit, what we do is that we kind of say that the driving is the smallest parameters in the system. I mean, it's the smallest time scale, smallest energy scale of the system.
Mm-hmm.
So the system bath coupling is greater than omega.
Okay.
So that kind of checks out that we are strictly in the adiabatic regime. And since we are considering weak coupling, so weak coupling, I mean, it already says that we are gamma is very small, right? And if omega is smaller than gamma, we are strictly in the adiabatic regime.
Okay, great, thank you. Are there any questions? So,
yeah, maybe I have. Yes.
Yeah, sorry, go on, Camille.
a small question, or yeah. So in order to derive your results, you use not approximation, but like the condition that the temperature bias is very small, so that you can use the linear response.
Mm-hmm.
And so I guess it means that if you don't use, or if you are not allowed to use the linear response, you are not able to write down all the properties of the machine in terms of geometric quantity. And
Mm-hmm.
so my question is, so what, I mean, do you have any like a kind of interpretation or physical interpretation? So what's the meaning of being able to write down, let's say, the work in terms of geometric property? Uh, so yeah, I mean, in other words, this breakdown of your results, do you have a physical interpretation why this is happening? Maybe it's a complicated question. I don't know.
Yeah, I mean, I don't know if I understood correctly. If I understood, I mean, you're asking why are you seeing the geometric nature in the adiabatic regime? Why do I need to choose the adiabatic
So
regime
no,
to see the
maybe
geometric nature?
to make it simpler, why when you are leaving the small biased regime, why is this result, why your result breakdown?
Ah,
What's
because
happening?
yeah, the point is that in the adiabatic regime, you can still follow the path of the instantaneous states, right? So it's a geometric character. I mean, what you do is that you need to have some sort of parallel transport, and parallel transport happens when you can't excite to higher states. You need to be following the same path around the parameter space. So at the end, what you see is that there is so if you have a phase lag between two different driving, you see there is a difference. And this gives you all the Berry curvature and all these geometric properties.
Okay, all right, thank you.
Okay, let's thank Bibek, and let's